Welcome back. The objective of this video is to complete an application problem of a sinusoidal function. So here in example 11, we say a buoy oscillates as waves go past. So when you're on the ocean, the waves go like this, and so the buoy goes up and the buoy goes down as waves pass. So this is kind of the path of the buoy going up and down. For any given time, it moves a total of 4.5 feet from its low point to its high point. So that's the total distance it covers from the high point to the low point, 4.5 feet, or as I like to say, 9/2 feet. And it returns to a high point every 15 seconds. So it goes through this cycle, and it takes 15 seconds to go from the low point and to the high point and back to the low point again. So that our period here is 15 seconds. So that is our period, is 15 seconds for one cycle. So 15 seconds per cycle. We've actually can answer question B right away. B says, what is the frequency of the motion? Well, if our period is 15 seconds per cycle, the frequency is equal to 1/15. So 1/15 of a cycle per second. And we'll talk more about this context in a minute. Actually, I'm going to take care of that right now. So we're going to say the buoy, B-U-O-Y, the buoy moves 1/15 of the path per second. So we've quantified that. So the buoy moves 1/15 of the path every second. Question A says, if the buoy is at its lowest point, t equals 0, write an equation that models the motion of the buoy. The key here is it's at its lowest point, or its minimum value at t equals 0. Well, a cosine curve is at its maximum value at t equals 0, and a sine curve is at the midline. We want to be at the lowest point. So what we've got here, interestingly enough, if we're going to start at our lowest point or our minimum value, this is going to be a negative cosine curve. So our equation is going to be some sort of y equals negative cosine of x. All right, so let's take a look at our diagram over here. We've got an equilibrium, which is our midline. Our high point and our low point covers a total distance of 9/2 feet. Well, the equilibrium is going to be the halfway point of that. So each one of these distances is going to be half of 9/2, and half of 9/2 is 9/4. So if we multiply that by 1/2, so each one of these is 9/4. This is our amplitude. So we know our amplitude is equal to 9/4. Well, since this is a negative cosine curve, we have y equals negative 9/4 cosine of x. Now, we're not quite done here because we don't have our b value. So we have to figure out b. So don't we know our period is equal to 2 pi over b? And our period is 15, right? It's 15 seconds for one full cycle. So 15 is equal to 2 pi over b. And solving for b, we get b is equal to 2 pi over 15. So now we have y equals negative 9/4 cosine of 2 pi over 15 x. And as we all have a tendency to do, I always use X and Y, but this is time, so I'm going to change my X's to T, and we'll do all that with respect to T. And that, we have successfully written a function that models the buoy's height as time passes. So I will go ahead and pull out the graphing calculator, and I will put my equation into the function. Let's think about our window as well in terms of our heights, how high we want to go, what our y values are, what our x's are going to be. If a cycle is 15 seconds, how long does our x-axis have to be? We have to think about all those things, and also consider that we have 2 pi over 15 as our b value here, and our angle is in terms of pi. So that is also going to be important. So let's go ahead and pull up that graphing calculator and input this into that and see what we can find. So here we are. We're going to input our function into the calculator. So I have negative 2.25 cosine, I with liberal use of parentheses, 2 pi over 15 x. So I should be in radian mode here. My window, my minimum x, since my cycle was 15 seconds, I'm going to go back to negative 5 seconds. I'm going to go out to 20. So I'm going to have a little bit bigger window here than 0 to 15. I'm going to count by ones. And my amplitude here was 9/4, or just 2 1/4. So I'm going to do a y min of negative 5 and a y max of 5. So that'll give me some breathing room to see that I only have to go up to 3 and negative 3. But this gives me some breathing room. So if I've got my function in and I hit graph and I just get this straight line. My calculator's in degree mode. I need to be in radian mode. So I have to change my mode. I go back down to radians. And now I graph my function. I get this really nice negative cosine curve where I began here at our negative 2 1/4, and then we follow the entire curve. And we want to find when we're at equilibrium. So when are we at 0? Well, we're going to be there twice. We've got 2 x-intercepts. So let's go ahead and find those zeros. So second calc 0. I got my left bound, my right bound, and I get a 0 at 3 3/4, and I'm going to get another 0 at, again, finding my zeros, do my left bound and my right bound. And 11 1/4. So we have twice we're at equilibrium, once on our way up and once on our way back down, until we get to our low point again here. So 2 different locales for equilibrium. So at t equals 3.75, we had an inflection point where our graph went from concave up to concave down. And again at 11 1/4 seconds, we went from concave down to concave up. And it should be no coincidence that we were 3.75 seconds away from 15 and 3.75 seconds away from 0, where our concavity changed or where we hit equilibrium. Let's take another look at that graph, and you can see that those 2 points here, we were concave up, and then we moved to concave down, and then we went back to concave up again at those 2 different locations. What does the equilibrium of the buoy mean in respect to the behavior of the waves? Well, the equilibrium of the buoy is also the midline of the function. The buoy is halfway between its maximum and minimum height. Identify the intervals where the buoy is decreasing. So where is our buoy decreasing? If we go back to our graph, our buoy is decreasing from half the time. And when it reaches its maximum height at 7.5 seconds, and till it gets to its minimum height at 15 seconds. We can find that max by finding the maximum within this particular range. So we find the max using our calculator. But we know, based on our characteristics of a cosine function, that that is going to happen at 7.5 seconds, and our y value, our maximum height, is 2.25. So as we saw in our calculator, the buoy decreases in height from 7.5 seconds to 15 seconds after reaching its maximum height of 2.25 feet. And this was going to occur every 15 seconds after 5 seconds. We'll reach that maximum height repeatedly as we continue through this cycle. And if we extended our graph, we'd clearly see that. So that wraps up this particular lesson, an application on concavity and a sinusoidal function, and you'll get some more practice with this when I see you in class.